What did Mars look like many billions of years ago? A quick Google search will give you pictures of Mars with a mostly red surface and large bodies of water covering it. But are these reconstructions really accurate? Well, it's important to remember that the early wet Mars covers quite a long time span. Generally, the geologic history of Mars is divided into 4 different periods: the pre-Noachian, Noachian, the Hesperian, and the modern period, the Amazonian. In contrast, the Earth's geologic history is divided into 4 eons, that being the Hadean, Archean, Proterozoic, and the modern Phanerozoic. Although, when you put these 2 timelines together, they hardly line up, mostly because not as much has happened on Mars as it did on Earth in the past 3 billion years. The pre-Noachian of Mars spans from 4.6 to 4.1 billion years ago, and roughly corresponds to the Hadean eon of Earth. With very little surface features left from this time on Mars, it's hard to infer what Mars actually looked like back then. We can safely assume that during the early part of the pre-Noachian, shortly after Mars formed, it had a molten surface. When had it cooled sufficiently for solid rock to exist on the surface? Well, zircons on Earth have indicated that by 4.3 billion years ago, the surface had cooled sufficiently for liquid water to exist, and, by implication, solid rock could exist as well. Given that Mars was smaller, and thus has a greater surface area to volume ratio, it would cool even faster than the Earth, so solid rock and liquid water could exist on its surface even sooner. Some speculate that both the ancient Earth and ancient Mars had a far thicker atmosphere than the modern Earth does, resulting in a higher surface pressure. This would allow water to stay liquid in temperatures of excess of 373 degrees Kelvin, or 100 degrees Celsius. In this scenario, both planets may have been covered in a global ocean of superheated water early on. If this was the case on Mars, it certainly would have been completely covered by clouds, with the surface being obscured. Looking at a topographic map of Mars, the most striking feature is the elevation difference between the northern and southern hemispheres. The average altitude of the southern hemisphere is 5 kilometers higher than that of the northern hemisphere. Why this dichotomy exists is one of the great mysteries in the field of astronomy. One theory is that the northern lowlands are in fact a giant impact crater formed when an object struck Mars near the North Pole some 4.48 billion years ago. Others hypothesize it was formed by internal forces such as a mantle plume. In this scenario, the crustal dichotomy would have formed later, but either way, it was certainly present by the end of the pre-Noachian. The next period, the Noachian, began 4.1 billion years ago, and while only 6% of the modern Martian surface formed during the pre-Noachian, 45% of it formed during the Noachian. As such, we can have a much better idea of what Mars looked like during this time period. Looking again to the topography of Mars, we know the hemisphere dichotomy was present at the start of this time period, and it's believed the second most prominent topographic feature on Mars formed at the beginning of the Noachian. This is the equatorial plateau known as the Tharsis Bulge. Volcanic outgassing from the Tharsis Bulge likely contributed to the atmospheric composition of Noachian Mars. However, the major volcanoes on the Tharsis Bulge, and ones who are located in close proximity to it, had yet to form. Instead, Noachian-aged eruptions from the Tharsis Bulge seem to have been in the form of fissure eruptions, and it's likely that Valles Marineris formed this way. Most Noachian-aged surfaces are in the southern highlands, and these are heavily cratered. During this time, both Earth and Mars were pelted by asteroid impacts, and the major impact basins such as the Argyre, Isidis, and the largest of all, the Hellas Planitia impact basins formed during this time. Noachian-aged surfaces show signs of erosion caused by rainfall along with the resulting rivers, and the impact craters appear to have had shorelines indicating that they were filled with water. We can see many paleo reconstructions of these crater lakes, but often they are surrounded by red rocks. The problem with this is Mars was likely not red at this time. On Earth, we famously have two kinds of rocks, oceanic mafic rocks and continental felsic rocks. The mantle is composed of the denser ultramafic rocks, and the crust was initially composed of mafic and ultramafic rocks. But over time, more of the lighter elements were incorporated into the crust, making it go from mafic-ultramafic to mafic. Once some of this crust was subducted by tectonic activity, the lighter elements would more rapidly melt, raising and accumulating in the area of the other plate near the boundary, forming the first continental crust. While Mars likely had some tectonic activity in the past, it was not as prevalent as it was on Earth. And even if it was, it doesn't appear that continental crust formed during the Eoarchean of Earth, which roughly corresponds to the Noachian of Mars, meaning the Martian crust would have been covered by mafic rocks during this time. Mafic rocks, being rich in iron and magnesium, have a grayish-black color. The red color on the modern Martian surface is due to iron oxides, and these iron oxides came about when the iron in these ancient mafic rocks were oxidized over the course of the past few billion years. So, it's likely that during this time, much of the Martian surface was a dark gray. Even though the major volcanoes had yet to form, smaller volcanoes were still widespread across Mars during the Noachian. So, if one was to stand on the Martian surface some 4 billion years ago, you might see a river flowing through a valley, a few volcanoes in the background, along with a few hydrothermal pools. However, these pools may not have been volcanic in nature, but serpentinizing systems, heated by chemical reactions between ultramafic rocks like olivine and pyroxene, and water. Well, that's what the surface terrain would be like, but what would you see if you looked up to the sky? For one, meteors burning up in the atmosphere would be a common sight. As for the extent of the cloud cover, while we know rain certainly occurred during the Noachian, how prevalent it was is still debated. Most estimates state that it rained less on the Noachian Mars than it does on the modern Earth. This would suggest that less cloud cover was present on the Noachian Mars, but since it had less gravity than the Earth, raindrops would have to get larger to fall, meaning that ancient Mars would have a greater cloud cover to precipitation ratio. So, it likely had comparable cloud cover to the modern Earth, where clouds cover roughly 50% of the surface. But what about the ancient Martian sky? Even though the modern Martian surface is heavily oxidized, the mantle seems to be more reducing than that of the Earth. Outgassing from this mantle would have enriched the Noachian atmosphere in gases such as methane and ammonia. High in the atmosphere, these would be subject to photochemical reactions, which would produce larger organic molecules, which would then precipitate out as droplets. This would in turn result in a yellow haze layer above the clouds, which would give the sky a yellowish hue. When lightning passed through such an atmosphere, it would also result in the production of small organic molecules dissolved in rainwater. This is what we call Miller-Urey type reactions, based on the famous experiment. In areas subjected to more thunderstorms, these organic molecules could accumulate, giving the surface and any bodies of water present a brownish color. Apart from the craters filled with water, the northern lowlands may have been covered with an ocean dating from this time known as the Arabian Ocean. What was this ocean like? The parts of the Arabia Terre which would have been covered by it are rich in phyllosilicates, suggesting it had a neutral to basic pH. In the oceans of the Eoarchean Earth, ferrous iron was a major ion, and this may very well have been the case for the Arabian Ocean, which, if true, would have given it a greenish color. Although ferrous iron is more soluble in water than ferric iron, above a pH of 9, it precipitates out as Fe hydroxides, so if the Arabian Ocean was more basic than that, it would be blue instead. But, say its pH was between 7 and 9. Asteroid impacts would readily produce giant tsunami waves, leaving large quantities of ocean water in low-lying areas near the coast. As the water evaporated, the concentration of metal and hydroxide ions would increase, raising the pH and causing Fe hydroxides to precipitate out. This could give nearshore pools a turquoise color at their bottoms, and any remaining salt flats a bluish-green hue. Such flats would be common in areas where there was a gentle elevation raise near the ocean in places like the southern Vestidas Borealis. Based on what we've discussed, what would Mars look like from space during the Noachian? Well, you'd see the aforementioned cloud cover and possibly the yellow hue caused by organic hazes. Below the clouds, much of the exposed land would be a dark gray, but glowing lava would likely have been visible at the bottom of Valles Marineris. The shallow areas of water such as the nearshore areas of the Arabian Ocean and the Argyre Impact Basin would have a greenish color, while the deep parts, such as the northern part of the Arabian Ocean and the Hellas Planitia Impact Basin, would have a darker color. There also likely was an ice cap over the South Pole. By the end of the Noachian 3.7 billion years ago, much of the surface water had disappeared, and much of what remained was locked up in glaciers. These glaciers would have covered most of the southern highlands and possibly the Tharsis Bulge. But this was not the end of the ancient wet Mars, for at the start of the Hesperian, the Tharsis Bulge again came to life. Massive eruptions formed in specific locations on and around it. Instead of fissure-type eruptions, these came from individual submerged magma columns, and as the eruptions continued, they gave rise to the major shield volcanoes on the Tharsis Bulge, namely Arsia, Pavonis, and Ascarius Mons, along with others in close proximity, such as Alba, and the largest of all, Olympus Mons. The more distant Elysium Mons would have also formed during this time. These eruptions released massive quantities of water vapor into the atmosphere, which condensed and rained down on the eastern part of the Tharsis Bulge. This water then flowed through Cassi Valles and Valles Marineris and emptied into the northern lowlands, creating huge outflow channels still visible to this day in the process. Eventually, enough water was released to form a new body of water called the Deuteronilus Ocean. Unlike the earlier Arabian Ocean, this ocean was acidic. After this fluvial event, precipitation became exceedingly rare on Mars, being 1,000 times less common than it was during the Noachian, and clouds would become far less common as well. This also meant that most of the craters would not have been filled with water. However, we do have some evidence of Hesperian-aged hydrologic activity in the Hellas Planitia Impact Basin. This appears to have come from meltwater near the rim, which would have then flowed into the crater as rivers. While it was unlikely that the whole basin was filled, some lakes were probably present in the deepest parts of the crater, located in the northwest. It was around this time that the Martian magnetic field began to weaken, and the solar wind began to erode the atmosphere. This would result in spectacular auroras, and would have stripped away any organic haze layer, leaving the sky blue. The solar wind would not only progressively thin the Martian atmosphere, but oxidize it, as the lighter hydrogen atoms were blown off away high in the ionosphere. This would also lead to the formation of diatomic oxygen molecules near the base of the ionosphere, as the oxygen atoms and sputtered water molecules recombined. This oxygen could then react with minerals in the crust. So it's likely that by the mid-Hesperian, parts of Mars, namely the older Noachian age surfaces, started to become oxidized. So, if one was to view Mars from space, much of the southern highlands, along with parts of the northern hemisphere such as the Arabia and Tempe Terra, would have developed a rusty brown color, while the younger Hesperian surfaces would still have a grayish-black color. It's also likely that the southern ice cap would have extended all the way to the southern rim of the Hellas Planitia Impact Basin. It's hard to say whether or not there was a North Polar ice cap during this time, because if there was, it would have been floating over the Deuteronilus Ocean and would leave little geologic evidence. But, given that the southern ice cap was more extensive than it is now, I'd wager that there was some kind of sea ice over the Martian North Pole. I think there's an elephant in the room. When discussing what ancient Mars was like, a question that inevitably comes up was whether or not it was inhabited, with some reconstructions of ancient Mars having bits of green as well as the red surface. But if Mars was inhabited in the distant past, would it leave visible signatures? If we again use the Earth as a reference, during the Eoarchean, we find isotopic traces of life, but no macroscopic structures. But, in the subsequent Paleoarchean, we find fossilized microbial mats or stromatolites. So, if Martian life followed a similar trajectory to Terran life, and that's a big if, there may not have been any visible signs of life during the Noachian. It's unlikely that Martian life forms would have made anything visible from space during the Hesperian, but it may very well have formed structures visible to the naked eye such as the stromatolites. If one was to stand on the shore of the Deuteronilus Ocean, they might find a few stromatolites in the shallows. Although, these probably would not have been as prominent as those we see in places like Shark Bay. Stromatolites form underwater and are only exposed by the low tide. Because Mars didn't have a large moon, its tides would have been much smaller than that of Earth. So, instead of fully exposed stromatolites, they may have been barely visible, being submerged by a few centimeters. Because the tides on Mars would have been influenced by the sun, the low tide would be during sunrise and sunset. As for the rest of the view you'd have, the beaches would be covered by black sands. Meteors would be a rare sight in the sky during this time, but you might still see a volcano in the distance. When the Hesperian ended and the Amazonian begins is a hotly debated topic, with some astronomers saying it's 3.2 billion years ago, and others saying it should be set at 2 billion years ago. This is because by 3.2 billion years ago, it appears that the Deuteronilus Ocean, along with all other major bodies of water, had dried up, but we still find evidence of hydrologic activity over the next 1.2 billion years. While precipitation would have been non-existent during this time, water vapor would still condense on glaciers, which would then melt and feed rivers. This gives us a gray area between the warm, wet ancient Mars and the cold, hyper-arid modern Mars. At this point, Mars would have been more frigid than it was before, with more extensive glaciers than today. This ice would not only cover the poles, but the high peaks of the major shield volcanoes. Even though volcanism would be waning at this time, some of these volcanoes could experience eruptions visible from space. As the surface continued to oxidize, Mars would look more and more red. There was likely a sort of color continuum, with the older Noachian age surfaces looking as red as those of modern Mars, while the surfaces which formed during the early Amazonian would be a rusty brown color. The whole planet likely appeared maroon from a distance. If one were to look closer, rivers flowing off glaciers might be visible from orbit, but instead of emptying into larger bodies of water, they would be endorheic, branching off into smaller rivers which ultimately evaporated. If one were to stand on Mars during this time, the surface might resemble some of the most desolate places here on Earth. If one was to visit the southern highlands, it may look something like Antarctica. Conversely, if one went to the northern lowlands, it would look much like some of the hyper-arid regions of western South America, with large salt flats and tiny pools present, all that remained of the Deuteronilus Ocean. Lastly, if one was to stand atop one of the major volcanoes such as Elysium Mons, it would resemble parts of Iceland, with lava erupting through snow and ice. As the atmosphere thinned and iron oxide dusts became more common, the sky would start to look like that of modern Mars, with a tan color close to the horizon and a deep blue straight up. Auroras would still be a common sight in the night sky. Around 2 billion years ago, the surface and atmospheric conditions of Mars closely resembled those of today. However, this is not to say that Mars was a dead planet, with nothing changing from then to the present. For one, there were some impacts which resulted in craters like the Mojave crater. Also, Mars experiences ice ages. Due to the lack of a large moon to stabilize its orbit, Mars tumbles more on its axis than Earth. This results in proportionately larger glacial events than that of Earth, which last millions versus thousands of years, with the polar ice caps spreading much further than they are now. Since its formation, Martian volcanic activity had been decreasing faster than that of the Earth, but it didn't simply stop 2 billion years ago. Olympus Mons' last eruption is estimated to have occurred some 25 million years ago, and a volcano in the Cerberus Fossae region, located between Tharsis and Elysium Mons, is estimated to have last erupted 53,000 years ago. Furthermore, a vast area located to the west of Olympus Mons, known as the Amazonas Planitia, was formed by a flood basalt eruption some 100 million years ago. So, Mars could hold some surprises in store for us in the near future. Well, that's my take on what ancient Mars was like. All too often, people reconstruct ancient Mars by putting water in the low-lying areas while leaving basically everything else the same. But, in reality, Mars was a very different world in the ancient past in more ways than having liquid water on its surface, and would have been pretty much unrecognizable when compared to the red planet of today.